Hello and welcome back to Calculus 1, section 5.2 on definite integrals. Wish I never said the title, right? Because I wanted to make the big reveal, right? But What do we have? In 5.1, hold on. So in 5.1, we learned to approximate area under the curve by creating the left rectangles, right rectangles, whatever, right? Have a lot of error. So let's use right side and have these. So now what I want to do is I want to go and cut each one of those rectangles in half, practically doubling the amount of rectangles. So what happens now? What happens is the amount of error immediately decreases. These areas where I'm placing red X's are no longer error. Those are no longer error. And then if I go with, let's say, orange and cut each one of the new rectangles in half, the error goes down even more. From this picture, I see a connection. More rectangles, less error. More rectangles, less error. So it's natural to think that if you are to use infinitely many rectangles, there will be no error. Now, why would that be so? Now, this is not mathematically correct what I'm going to do, because that's not a proof, but it's so easy to understand. So I'm still going to do it. Probably at least half of my department will shoot me point blank for this, but it's such a good thing to understand, so I have to. Why is this bad? Because you cannot determine which point is next to which point. Because you pick any 2 points, the way the number line works, if you're not familiar with that, is that if you pick any 2 points on the number line, you can fit infinitely many points in between those. So there is no way, comma, in hell, comma, to pinpoint 2 points that are next to each other. Because as soon as you pin 2 points down, you can put infinity of the points in between them. So that's an issue, right? So just because of that, what I'm going to do now is wrong. However, it kind of paints the picture of this. If you have infinitely many rectangles, you actually get area under the curve. Because let's say that I'm interested in area under the curve between A and B. And let's say that by some magic, I am able to determine points that are next to it, right? If I make my delta x so tiny, so width of each of the rectangles is technically 0 because it fits under a single point. I can paint this by, you get a point, and you draw the rectangle down. You get a point, draw the rectangle, point, draw the rectangle, point. Do you see how I'm going to canvas everything? So infinitely many rectangles is going to be exact area. And all I need to do now is to work out mathematics of it in terms of formulas so we can use it. Now, I need you here with me mentally, please. If I pick a representative rectangle here, which has delta x width to it, can we please agree that the area of that rectangle would be f of x, I'll call it this f of xi, because it's somewhere, right? This I is a counter, it's some x somewhere in the middle, let's say. So f of xi times delta x. Do we all agree that this is area of a single rectangle? You have the height times the width. Are we agreeing on that, right? Now what I'm going to do is I'm going to introduce a mathematical symbol, summation. So this symbol means sum. And I'll explain this. I'll explain the details about this symbol. So summation. So let me do this. So this over here is one rectangle. One rectangle. That's all it is. But now I am going to start. I goes from 1 to n. And I'm going to say that this over here is n rectangles. So I have area of a single rectangle, and now with this summation, I have the area of the many rectangles. Guys, this over here is equal to your 5.1, because 1 to 6, that's 6 rectangles. 1 to 10, 10 rectangles. 1 to a million, million rectangles. Finite amount of rectangles. Finite amount of rectangles with this sum. And I'll explain the sum as soon as I'm done with this formula. The only thing that I need to do now is to shoot this n to infinity to make infinitely many rectangles. Now, how do I do that? I put the limit n to go to infinity. And this is now infinitely many rectangles. It's a three-step process. You write one rectangle, then you say, let me add more rectangles, and then let me add infinitely many rectangles, right? So it's a development. You know how to calculate one area of the rectangle. That was what, grade 3, 4, whatever, right? Calculating area of the single rectangle, and then calculating area of multiple rectangles to add them all together, which is why we use the sum. And then, but the sum had a finite amount. This n is a finite amount. It's a 6, or it's a 10, or it's 100, or a million. It's a finite. And then what I do is I send that n to infinity to include infinitely many rectangles. Now, do you remember what happened with delta x? What was the formula for delta x? Please. B minus a over n. So, how big is delta x now when n goes to infinity? Extremely small, going to 0, right? As the number of rectangles, because n goes to infinity, right? Delta x has n in it. Well, we have the formula. So, as the number of rectangles goes to infinity, the width of each one starts shrinking down to 0. So, you are technically adding infinitely many, infinitely thin rectangles, which is why I said under each point you have a rectangle that kind of fits, and then, right, infinitely many of them. They canvas the entire area, and this is what it's called exact area. This is what it's called exact area. Now, we have a very special notation for the exact area under the curve. And it involves your good old friend integral. Integral a to b of f of x dx is equal to the limit n goes to infinity of the summation from 1 to n of f of xi delta x. This is called Riemann integral, and it's used to calculate area under the curve and to calculate exact area under the curve. Riemann integral. So it's about 100 plus years after Newton's derivative and conceptualized calculus with derivatives and so on. Newton was aware of antiderivatives, but these are not antiderivatives, guys. This is a definite integral. This is a different creature. It doesn't have plus c. These are going to give you numbers as answers, because area under the curve is 7 or area under the curve is 10, right? So it's a finite value. So Newton was aware that if you differentiate a function, in his case a polynomial, that you can do the antiderivative and you can go back. But he never had it as the area under the curve. Now, why is this important? He calculates a lot of stuff. Any kind of accumulation that you want to calculate, because you see that sum, right? What is sum? Sum is accumulation of stuff. If you want to know the amount of energy in a system, you integrate, because energy is going to be area under the curve. If you want to know how many new people were added to the planet from 1987 to 2002, it's going to be integral between those years of the population function. So this stuff calculates accumulation. The easiest application to understand is area under the curve, but in general this formula calculates any kind of accumulation, which is why this is one of the most important formulas of all of STEM and finances and everything else, right? How much money did I acquire over a period of 3 years? What is the amount of rainfall in the last 2 months, right? Well, it rains one day a little bit, then waits for like 2 weeks, and then rains more, right? Then it waits for 3 days, then it rains 7 days in a row, right? So what is the total amount of rain that I get in a certain area? All of those concepts are calculated with something like this. Before we go and do any of the problems with this, we are going to briefly look into the summation notation with the sigma, with the sum. So this letter is pronounced as a sigma. It's a Greek letter, and it means sum. Now, guys, all this is a way out for lazy people. All right. Instead of writing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, I can just say add all the numbers where the numbers start from 1 and end at 7. That's all it is. It's a lazy notation. You see that I have ability to write it out, right? But then I just want to use it in this compressed form so I'm not annoyed. can I have summation of 2i plus 1? I starts at 0 and goes to 3. Sure, I just have to work out all of these 4 digits, right? It's a counter. Start at 0, 1, 2, 3. You have to end on top, right? Number. So 2 times 0 plus 1 plus 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1. That's what it means. We don't have to go computing this thing. It's just, I'm interested in what it means. Summation, I starts at 1, ends at 5, for I squared. Great. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. You can have any formula you want inside summation. You will go one by one on each one of these digits that are counters. This is where it starts, the first integer to plug in. This is where it ends, right? So that's all it is. Now, summations are a bunch of addition, and you can factor. So if you have summation of some kind of a constant times some function of this I, you can kick the constant outside. You know that you can kick 3 in front of the derivative, you can kick 3 in front of the integral, you can kick 3 in front of the sum. But here is the coolest thing. The coolest thing. You've seen this with limits, but still. The variable here is 1 to, let's say, 3, and then 1 to 3. You see, summation operates on i's because that's its counter. So if I have a summation of, let's say, 3 divided by n times I, and I goes from, let's say, 1 to 8, I can kick 3 over n outside because n, in this case, is not a variable of a summation. Right? Do you remember when you guys had to take the limit h goes to 0 of 2x plus h minus 3? What was limit operating on? What was limit killing here? It was killing just the h, right? It never bothered 2x or a 3. Right? Because the variable in the limit was h goes to 0, not x goes to 0. So if I have a multiple variables here, n and I and k and z, the only one that you cannot kick out is the one that it's actually used as a counter. The rest you can kick out. So it only operates on the variable that is a counting variable for that particular sum. Summation n goes from, let's say, 2 to 19 of 3 over n I. You get to kick 3i out and leave 1 over n inside because now variable is n. So it's very important, which variable you are using as a counter, which is why I told you earlier, that dx, you have to have it every time because you can have a dy, you can have dz. So it's important to know what variable you are differentiating and integrating in respect to, and in terms of sums, what are you summing over? It's all the integers in this case. You can split summations into multiple summations. So if you have a summation of some kind of a function plus minus some other kind of function, each one gets its own and keep plus or minus. So this is another standard rule that you guys have seen with limits and derivatives and integrals, right? It was in blue. So for summations, you have the same deal. Now, why do we cover these things for summation? Because the formula over here has a summation in it. Do we all remember the limit definition of the derivative with h goes to 0, f of x plus h? That was called the limit definition of the derivative, right? What you're looking at over there is its equivalent for integration. That's what you're looking at. Now, you also remember excruciating pain, right? Calculating that limit, right? Which is why we invested so much time in chapter 3 learning all those shortcuts. So you don't have to crank that limit. Your product rule and quotient rule and chain rule and logarithmic differentiation, that's all developed and figured out so that we never have to do that limit, right? Well, what did you learn last lecture? I mean, 2 lectures ago. You learned all of the shortcuts for integration. Why? Well, so you don't have to do what follows next, okay? So now, what we're going to do is area under the curve let's say f of x is equal to 3x plus 4 on 0 to 2. That's it. Let's go. Area under the curve 3x plus 4 on 0 to 2. Well, what's my delta x? My delta x is b minus a divided by n. It's 2 over n. I'm not going to do 4 rectangles or 6 rectangles. Remember that I'm going to send n to infinity. So I keep it as n now. I keep it as n because I'm going to send it to infinity. So my delta x now is in terms of n. What else do I have? Well, I have to figure out that ci. Remember the formula, the xi, sorry? Remember the formula that I had earlier, which was a plus I delta x? Yeah. So a is 0 plus I, and delta x is 2 over n. So the whole thing is, let's go 2 over ni, or I, it doesn't matter. Please don't confuse this I with a complex I, has nothing to do with it. Maybe you want to write that in notes. This I has nothing to do with a complex I. This is a counter I, which takes on, so let me just write, this I here is simply 0, 1, 2, 3, 4. It's just counting numbers. That's all it does, count numbers. Now, what is my f of xi? Well, that's going to be 3 times 2 over ni, because that's my xi, plus 4. So now when we work this, we get 6 over ni plus 4. Finally, I have all building blocks so that I can plug them into the area formula. Limit n goes to infinity, summation 1 to n, and here I have my function, which is 6 over ni plus 4 times delta x, which is 2 over n. So limit is the limit, summation is the summation, this is my f of xi, and this is my delta x, and you go look at the formula. Right? Look at the formula. So you know where all of this was plugged in. Guys, this is 100% setup for every problem of this kind. You find dx, you find xi, you find f of xi, and when you have all those building blocks, just shove everything into your equation. And now, all we need to do is to solve this, right? Limit n goes to infinity, summation 1 to n. The only thing I can do here is to multiply this in. So I have 12 over n squared I plus 8 over n. And then I know that I can split this now into multiple sums. So I have summation 12 over n squared I, where I starts from 1 goes to n, plus another summation where I starts at 1 goes to n, 8 over n. For the first sum and for the second sum, I can kick out in front of the sum anything that is not I. So 12 over n squared gets kicked out and I stays in, plus 8 over n gets kicked out and just number 1 stays inside. So this is what we have. Again, very structured. Very structured. Steps are always the same. You just have to be careful with what kind of formula functions you have to plug everything in. So next step is to use the formulas that are provided to you in a textbook, in the 5.1, when they discussed. I didn't talk about these formulas. I think they're on page 345. Page 345 has that box that converts these sums into algebraic expressions in terms of n. You have 4 of those for a constant I squared, and I cubed. In the case of the book, you're using k's. So page 345 in the new book, but whichever book you have, it's going to be in 5.1. So now, limit n goes to infinity, 12 over n squared. Now, my I over here turns into n plus 1 over 2. So I'm going to actually circle these as a pair and say formula, page 345. Then we have plus 8 over n. And then this is going to be just 1 times n. And I'm going to again circle these 2 puppies, forgot to close parenthesis, and say formula, page 345. So now, limit n goes to infinity, 12 and 2 cancels, and you distribute everything up there. That's going to be 6n squared plus 6n divided by n squared plus n and n cancels, you just have 8. The limit as n goes to infinity These have the same exponent, so it's just 6. 6 plus 8 is equal to 14. Exact area is 14 from this calculation. Woohoo, huh? You wish you had your limit back for derivatives at this point in life, because the simplest problem that I have, which is a linear problem, took a page and a half, right? Quadratic problem, cubic problem, right? Now,
so 6 comes from numerator.
Canceling 12 and 2, yeah.
Yes.
And then we multiply. Is there another way? Well, of course. Riemann integral. Riemann integral on the same problem. What was my problem? It was 0 to 2, 3x plus 4. dx. Hey, we know how to integrate this stuff. Copy the 3. What was the integral of x? X squared over 2. Great. And what was the integral of 4? 4x. And now, here's what's new. You put a vertical line 0 to 2. That's new. You don't have plus c now. You don't have plus c. You have a vertical line because you have to compute at these limits. So now, the way we compute is we plug in the upper number, and then minus, we plug in the lower number. So this is going to be 2 squared over 2 plus 4 times 2 minus 0 squared over 2 plus 4 times 0. It looks like 40. There we go. And now we compute. This better come out to be 14. So I have a 6 plus 8 minus 0, which is 14. Now we can do the game that you do when you go to your eye doctor. What's better, A or B? You know how it go? What's better, A or B? A or B? And then you pick B, right? Because you know the way to integrate, and on top of that, now you have to learn to compute the values. So now, going back to our notation, here comes the red. Area equals integral a to b of f of x dx is equal to the antiderivative, that was capital F of x, right? This is why we had that notation. And look at the formula. It's f of b, antiderivative computed at b, minus f of a, antiderivative computed at a. This is the definite integral and this definite integral is always equal a number. We just got 14 earlier, right? So I just have a few remarks about this. If you studied what we did before, known as differentials, do you recall something like this? You do recall something like this from differentials, right? Hopefully. So, if I'm to write limit n goes to infinity of summation of f of xi times delta x, do you see that's that? Do we see there is a function and a function, there is a dx and delta x, right? And what does this symbol remind you of? And what does it stand for? The squiggly line, what is it? This symbol here, guys. What is this? Yeah, squiggly line. What does it look like? Come on. What does it look like?
An F without the line in the middle.
Huh?
An F without the line in the middle.
An F without a line in the middle. Okay, that's the first one. I've never had that one before.
It looks like.
It looks like. Yes, it looks like an S.
Close.
There's the transformation, right? And what S stands for? Sum. Exactly. S stands for sum. Unless if you're from kryptonite, then it's from Krypton, then it stands for hope. But in this case, it stands for sum. So there you go. Look at the link. Right? I know, right? What is original notation from Riemann? Original notation was S P comma U equals to blah 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 blah. That was the original notation. S P and U, German words. I'm not sure. Well, maybe it was UP. I don't know. It's PU or UP. I'm not sure which way it was, but it's one of those. And one stood for upper limit and one stood for lower limit. So if you wanted to write your integral, it would be S0 to, right? And then you put your function here, 3x plus 4, right? So that was the original notation. Now over time, we developed that into a better notation that we use today. So what is the integral? The squiggly line is just an S. Squiggly line is an S, and you see all of these. Now, guys, do you remember that this part over here was the height times the width? Right? So now, you tell me, conceptually, what happens if I write garbage like this? Is this even remotely anything? And the answer is no. What's missing? No dimensions, right? It just cannot be at all, because it's missing dx. It's times dx, and dx is the width. You want your height times the width to get the rectangle, and you call that an area. If you don't put dx, you just ruin the whole thing. Right? So you're making the soup and you didn't put any water in it. Really? I mean, okay, you didn't put any liquid in it because I have to cover my Slav brothers, we cook with vodka. So there is your integral, and this is a definite integral, and a definite integral. The calculation inside is the same as 4.9 with the added step. Instead of plus c, you put this line, you put the limits, and then in this function, you compute the upper limit first, and then the lower limit. So I know that class ends in 1 minute, but I just need to go through one example, and I'm going to make it a trig, just for a good measure, right? Because I know how much you love trig. So what is the integral, right? What is the integral of, let's say, sine x dx from pi over 6 to pi over 3? Well, first you need to tell me what the integral of sine is. Negative cosine x. Very good. We put a vertical line, pi over 6 and pi over 3. Now we go negative cosine of pi over 3, which is called the upper limit. Upper limit. And then you have minus from the formula, and then you have your negative cosine of pi over 6, which is your lower limit. So now you cosine of pi over 3 is very good, plus cosine of pi over 6, excellent, for a total of root 3 minus 1 over 2, about 0.4. This is about 1.73 minus 1 divided by 2, so about 0.35. That's the answer. We don't care. We want the exact, right? Because this is calculating exact area. On my graph for sine, I have my pi over 6, I have my pi over 3. This area here is what we have. The story is not over. We'll have to continue next time. There are issues that we have to worry about, which naturally leads into the next lecture, and the next lecture is called Fundamental Theorem of Calculus. Might be important, huh? Since the title, Fundamental Theorem of Calculus. So we'll talk about these things on Monday. So I'll open the homework, make sure you do some work, and I'll see you Monday. Bye.